Good morning, good afternoon, everyone. So today I'll be presenting our ongoing research for the submission for the IEEE CEC 21 conference on June 28th at Krakow, Poland. So this work is demonstrating a complexity-based lambda layer for time series prediction. I'm Kenneth Brzezinski and I'll be presenting this presentation on behalf of the University of Manitoba. So the presentation overview, I'll just quickly go over the problem overview and what sort of time series analysis we're looking at. Methodology will present our novelty and what we propose in our work. Thirdly, the results, and finally the conclusions and future work. So just a quick overview. Since our focus of this paper is on time series, it'd be worth going over time series and what exactly that is. Time series analysis is focused on the analysis of data in some sort of sequence and in the temporal domain. Examples include things like internet packet data, so internet packet data coming into a server or out over a discrete time interval. Weather trends, any sort of time interval can be days to seconds to microseconds to years, so weather trends over the years would be an example, and any other data that has discrete time intervals to explain some sort of phenomenon, and that's what we're interested in. So at the figure at the bottom I just have an illustration of, for example, an electrocardiogram. Electrocardiogram is the way that we measure the electrical signals in the heart, and each of these correspond to a heartbeat. So that would be an example of a time series where over a period of seconds or a minute or so you display a certain number of heartbeats, and we can sort of pick up that data in discrete time intervals. When it comes to time series analysis, there exist already several techniques in order to extract these features from signals. Two very commonly forms are Fourier analysis and wavelets. So Fourier analysis is well popularized. It's been something where you're just turning the signal into the frequency domain and extracting features in that way. And wavelets is something that is well developed but more recent. And pretty much the purpose of time series analysis is that our goal is to look at past data and to use that past data and the features contained with it to make future predictions. And that is sort of the essence of it. And the idea is that if you're able to do this, well, the signal is said to exhibit in some forms long-range dependency. And I underline the word long-range dependency because it's sort of the ability to pick up features in data, and then those features can have dependency in the future. So the future signal also is dependent on the earlier signals. And this sort of follows with how everything works in nature. Everything is a chaotic system. Everything is a function of past behavior. It's just a matter of, do we have the techniques available to us in order to extract those features? Are our measurement systems sensitive enough? And so on. So at the bottom here, I just have two examples of some time series analysis. For example, on the left, we have white noise. So white noise has no pattern contained within. So no matter at what point you look at the signal, it sort of looks distributed, it looks random, and there's no way you can make prediction of the future elements of the time series. As opposed to a sinusoidal wave, we know that it's governed by an expression, by an equation, and therefore wherever you are along the time series, if we were to consider it as a function of in a time series, well then you could predict exactly where it'll be in the future. And it also, to our eyes, exhibits periodicity. We can see that there's a periodic nature to how it goes up and how it goes down, and just the general behavior. So this introduces us to our problem statement. So can we develop novel techniques in order to incorporate long-range dependency into our analysis of a future time series? So in the figure on the right, what I have is Brownian motion, shown as the red noisy signal, just showing that it's sort of monotonically increasing from left to right. So this is Brownian motion has an element of randomness included in it, but not to the same extent as white noise. And the other thing we want to look at is, can we integrate previously known techniques, for example, temporal sequencing models, such as recurrent neural networks, and can we take these existing models, which look at the past behavior and try to make future predictions, can we improve the performance based off of our incorporation of long-range dependency? And in the figure, we have the blue signal that looks noisy as well, that looks like random noise. Well, it's actually the fractal dimension. So this leads us on to our next slide of what exactly a fractal dimension is. Well, fractal dimension is the idea that no matter what, if you look at certain elements in nature, It could be a time series, it could be some other sort of structure, anything that contains information. It tends to have this idea of self-similarity, the idea that you can look at the information that you're looking at different scales, smaller and smaller scales, and then what you see is you'll see relationships, and those relationships are consistent, and they tend to follow a power law relationship. So in particular, we're looking at the variance fractal dimension, which looks at the idea that if you're looking at smaller and smaller scales of measurement, what you'll see is that the variance fractal dimension, variance of the signal, follows the power law relationship when you're looking at larger and larger scales. So you're looking at scales, let's just say really small scale, the nanoscale level, and then the microsecond level, and to the second scale. And then what you'll see is you'll see that power law relationship as a function of the variance and the scale that you're looking at. So there's a quick way that we can sort of analyze the variance fractal dimension. It's something that can be done online, where you're given a sequence of signal points, let's just say y, and then you can actually take the variance by looking at every other element of the time series, which is shown in these white circles, and then you can subtract them and take the square, and what you get is the measurement of the variance. So on the right, we have two expressions, one at the top being evaluation of h, which is the Hurst exponent. And this, what I was explaining about looking at different scales, is pretty much what is governed in this equation. So if you take the log of the variance of a signal, and then you take the log of the scale that you're considering, again, scale just meaning smaller and smaller scales or larger and larger scales. If you see the limit as tau approaches 0, or as that scale approaches a single element, what you'll see is that the log-log relationship will produce a value called the Hurst exponent, and then that will produce something called a log-log plot, and then you can extract the fractal dimension based off of the slope of that log-log plot. So at the bottom we have d sub sigma, which just is the actual measurement for the fractal dimension, and that's just calculated from f plus 1 minus h, f being the embedded dimension, or how many dimensions is the signal contained in. So if you're only considering one feature in time, it's a one embedded dimension. So it would be 1 plus 1, 2, subtracted by the Hurst exponent, meaning the value is somewhere between 1 and 2. So it's embedded in a one and a two-dimensional embedding. So this sort of covers exactly how we aim to introduce our variance fractal dimension into our model. And what we do is we're actually setting up as a lambda layer on existing temporal and non-temporal ANN architectures. So it's very simple that we can take existing architectures and then we can actually add on at the front end our variance fractal dimension based off of the signal that's coming in. So a signal comes in, the variance fractal dimension is computed on the fly, and then we can pass it into these models. So one of the other things we can do is we can dynamically determine our root mean squared error on the predicted output and then compare it to the validation set. What this is sort of just suggesting is that when we're actually making future predictions, typically when you have training and validation data, you have training data coming in and you're validating. And then you have more data coming in from the validation set, and then you're predicting, again, the next element of this signal. So because we're computing the variance fractal dimension on the fly, what we're actually doing is we're making predictions based on our variance fractal dimension and then computing the variance fractal dimension as those predicted outputs come in. So it's done on the fly, so it's done dynamically. So just to introduce to our data set, we produce synthetic Brownian noise according to the Wiener process, and this is just a matter of we're taking previous elements of the signal and adding an element of randomness, of random noise, and this produces Brownian motion. And then what we do is we determine the variance fractal dimension from the data set for each stationary frame. So when you're considering how much data we're going to use to determine complexity in the form of the variance fractal dimension, what matters is the size of that interval. The size of the interval is important because the smaller and smaller of a frame that you look at, the less important it is. If you're only considering one point at a time, you can't determine the information contained in the self-similarity of multiple scales of one point. So it needs to get larger and larger, but as it gets larger and larger, the data set itself becomes non-stationary, so it has a changing mean and covariance. So for a stationary frame to be stationary, we'd have to make sure the mean stays the same as a function of a small time interval tau, and also the covariance is the same for the stationary frames to be stationary. So just as some preliminary results, what we have is tested on an ANN architecture. So on the very left, we have red and blue circles, which just represent our input neurons. So the blue can just be our time series data, and the red being the variance fractal dimension. So those are fed in as two featured inputs. That's a function of W being the window size. So that's sort of the size of the tensor that you're working at. The window size is a function of two features per training batch. We also, just for this preliminary work, looked at the hidden dimensions of 64 and in one layer of hidden dimensions, and then finally output Y. What I want you to focus on is, as in the x-axis, is window size. So how many, or W, how many points are you looking at in order to make the future prediction? So we can look at the last 3 points of window size of 3 and make the next prediction, or we can look at more data, for example, window size of 10, and then make the next prediction. What you'll realize is that performance actually degrades, at least for the synthetic brown noise, when you have larger window sizes, and that's because there is no incorporation of temporal information in a non-temporal ANN architecture. You could look at the last 100 points of Brownian motion and it won't tell you anything about where it's going to be in the future. But because the Wiener process is based off of the previous points, the smaller and smaller window size you go, the better the predictive capacity becomes. And the main takeaway from this is that on the y-axis, we have the time series at the bottom and complexity and time series. So complexity and time series for the rest of the presentation just refers to adding both features of the time series and the variance fractal dimension, as opposed to time series is just the time series itself. So no matter what the time series is, window size is, when you incorporate complexity built into your time series analysis, you'll see that the predictive and true values are very close together, and the root mean squared errors demonstrate that it performs very well. So again, one of the other things that we looked at was we took the same non-temporal architecture, but what we did was we changed values of tau. So in a few slides previously, I had mentioned that you don't want to look at one point of your variance fractal dimension because it doesn't give you enough information about the self-similarity. But as tau increases, you can incorporate more information about the self-similarity, but again, you're expanding outside of the stationary frame. And you're also incorporating more information about previous data that maybe isn't important to make the future predictions. So this figure just demonstrates that as a function of window size of 3 and 10, and as a function of interval size of 16 and 64, meaning the last 16 points, the last 64 points, interval sizes of 64 outperform those of smaller interval sizes of 16. And we also tested values of 128, and they worked quite well, but as you get larger, they become non-stationary and they tend not to perform as well. So this introduces us to our temporal analysis. So temporal analysis just means any type of recurrent neural network architecture. So here in our hidden dimensions, instead of just having a dense layer, what we have is BD, bidirectional, LSTM, long short term, or D for dense. So we have the same input output as previously, except in the middle we have one or more sequences of stacked hidden layers incorporating bidirectional LSTMs or dense layers. And the hidden layers that we tested was 64, 128, 256. And again, tau varies between, in this analysis, 64 or 128. So the focus I want you to have right now is just at the top plot and validation root mean squared error, where lower is better. So if you look at all these plots, what I want you to focus on is the hash plots that go horizontally, so not the time series, which are just the dots, but the complexity, which are hashed. If you look at the 10 best performing models, which again is the lowest validation RMSE, what you'll notice is that 7 of the 10 performing best models incorporate complexity in some way. And the reason why time series is also represent 3 of those 10 models is because we're also testing different RNN architectures. So some RNN architectures with more capacity outperformed ones with lower capacity with complexity. So that's just to demonstrate that 7 out of 10 of the best performing incorporated complexity, which is important for us. And the bottom plot, what I want you to focus on here, is that the x-axis, what it has is 4 different RNN architectures. So they each have some sort of combination of different dense layers, LSTMs, bidirectional layers, and also they all have 3 separate layers. What I want you to focus on is that on the very left, the architecture that was 128 bidirectional, 128 bidirectional, and 128 dense had the most best performing models included in that RNN architecture. And that's because as you add more and more capacity with more and more dense layers, doesn't necessarily mean you outperform, because you tend to overfit. So the takeaway I want you to find is that we looked at window sizes ranging between 3 and 15. What we noticed is that window sizes of 10 and 15 worked quite well for us. And again, these are the same plots that are shown at top, just color-coded to display window sizes. And again, 7 of the 10 best performing models that we found with the lowest validation RMSE incorporated complexity in some way. And finally, the last results we wanted to look at was, okay, given that we have making future predictions based on our data set of time series and complexity, as the validation set is predicted, we're going to take those predicted outputs and compute the variance fractal dimension on the fly. So here I want you to focus on the bottom 2 plots in particular. The top 2 plots are actually just the entire time series of the validation set. The bottom 2 plots are the zoomed in version of just say 50 or so points. So for the main takeaway, I just want you to focus on the bottom 2 plots. And these bottom 2 plots just represent window sizes of 7 and 10. So similarly, we have just a simple hidden layer size of 128 bidirectional, and a tau of 64 for all these plots. So what I really want to demonstrate is that if you look at the trend of complexity, which is the red plot, and its 95% confidence interval, what you'll see is that it follows and covers very well the validation set in some way. It's smoothed over, and that's because it's summed over 12 to 15 trained models, so it's summed over, so that's why it's smooth and not as noisy. But overall, the 95% confidence interval and the average follows very well with the validation set for a window size of 7. And the reason why the confidence interval is so large is because from model to model, it's making those predictions on the fly, and the model itself have different architectures with different sets of weights. What you'll see is that you see lots of variance. As opposed to if you're just looking simply at the time series, it has its own confidence interval, which is much tighter, but that's only because with a model trained on the same training set and validation set, the only variance has to do with the weights and sort of what those weights converge to. If you look at the window sizes of 10 on the right, what you'll see is that the complexity actually did not outperform the time series. And if you looked at the root mean squared error, which is in our paper submission, what you'll find is that it doesn't follow as well with larger window sizes. So what we take this as is window sizes that are smaller, closer to 5 or 7, tend to outperform the time series because it is looking at less information previously. So when you're also looking at a window size of 7 or 5, for example, what you're also looking at is the last 5 complexity fractal dimensions incorporated in that prediction, right? So just because you're given more and more information doesn't always mean the prediction is the best. And what we found is that with smaller window sizes, closer to 5 or 7, with the added feature of complexity, it outperformed the time series. So just finally, as a summarized conclusion, what we demonstrated was when we incorporated complexity lambda layer, we found that when we incorporated for non-temporal, just dense layers, and temporal RNN architectures, what we found remarkable improvements in the validation RMSE. And when we added that lambda layer, again, just as a front end for this RNN architectures, we tested it with taus of 64 and 128, and we varied window sizes between 5 and 15 with values from 5 to 7 to 10 to outperforming the rest. Again, it totally depends on the RNN architecture, and it's a use by use case. But what we found was when the lambda layer was incorporated dynamically, that is to say, we make future predictions, and then based on those future predictions, we compute the variance fractal dimension on the fly. We found that it did have advantages over considering just the simple time series alone for certain window sizes, and again, certain values of tau. So with that, I thank everybody for following my presentation. If you have any questions, just send them to my email. And with that, I thank everybody for watching.